Okay, so we have to show this. By the way, before we even begin, if you accept that the distributed property is true, the distributed property is this: A union B intersection C is same as A intersection C union B intersection C, and then A intersection B union C is A A union C intersection B union C. So these are called distributed property because it's as if like if this is like A plus B times C, the right side really, if you think about this like the multiplication operator and this like the addition operator, then if you write down the usual distribution property, which is AC, A times C plus B times C, this reads exactly like that, okay? Yeah. The interesting thing is even if you switch the union and the intersection around, you still have a distributed property. So that's an interesting property of a set. And if you just take this one and replace B by B bar, then you get exactly the same identity. So it's kind of knowing the distributed property makes the proof of this kind of moot. But let's say we didn't know that, and we have to show this using the either the Venn diagram or using the truth table. Okay, so let's first try the Venn diagram way. In Venn diagram for three objects, you have to write this picture because that's the generic form of the of three sets inside some universal set. And then first of all, you have A union B. So here's A, and then here's a, wish I had a different color. Here's B bar, this one here. Okay, so this is B bar because it's the set where it collects everything that does not belong to B. So it's outside of B. Okay? So that says if you do A union B bar, you end up with you get this one and this one here. Okay? So the only place that's not shaded is inside B, outside of A. Okay? All right, so now you do intersect this by C. Imagine what you get. You end up with A union B bar intersect C. That's going to give you A, B, and then C. The only portion of this shaded area that belongs inside C is going to be this much. Okay, there's going to be C. So that's what we find from one place. That's the left side. On the right side, and when you're trying to show by a bunch of Venn diagrams, you should really spell them out. I guess this one was really just explained, but I would like to see at least these two. Okay, these two pictures should be, because I need to see how you arrived at this set. Okay, now what about A intersection C? So if you have A, B, and then C, A intersection C is going to give you this much. And then what about B bar intersection C? So here's A, here's B, here's C. What's B bar intersect C? Well, it's B bar is everything outside of B, and inside C, look for the ones that's outside of B. So you end up with this much. That's going to be B bar intersect C. So intersect C means you're only looking at the ones that are inside C, but B bar means it has to be outside of B. So these are the ones. And then you now put them together, which means both you combine the two shadings, right? So now you have A intersects C, union B bar intersects C, that's what you get. And then since this one is here, that one is here, the resulting picture is this, which is exactly the same as this one, right? So by the Venn diagram, we've shown that the two sets are equal. Okay, so now let me show you this second way of proving the equality using the truth table. So here the truth table means you're imagining some x where the statement x belongs to this set is true or false. Okay, so if you have t, 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 this will be an element that belongs to all of A, B, and C. So in the Venn diagram, that will be the case when you have A, B, and then C here. Okay, that's going to be the intersection of A, B, and C. Okay. Now it could be you could also have T, T, F, and that's the case where it belongs to A and B, but does not belong to C. So that's this case. Okay. So by just choosing some sequence of T and Fs, you can talk about every region in that Venn diagram. Okay, that's why this type of argument works, because it figures out all the possibilities of an element. Okay, and you would need to write down all the possible sequences: FTT, FT, FTF, FFT, FFF. Okay. And for each one of these, I need to compute this, this, this. Oh, I need to compute this because that's going to compute this. And now you have to intersect C, and this is going to compute the left side. And for the right side, I'm going to compute this one, and I have to intersect, I have to take the union of those two, and I'll get something, okay? And we show that the two things are the same if the TF sequence that you got from these two columns are exactly the same. Okay? Then that means they're describing the same set. Okay, so let's try this one. When is union evaluated to false? When does union evaluate to false? Remember, this is OR, right? So OR operator gives you false only when both are false. Both are false. Okay, so but since it's B has a bar there, we need to look for when this B itself is true and A is false. So let's look for A false and B true. It's actually these, right? Yeah. So those are the only cases where the A union B bar is going to evaluate to false, and all the other cases I'm going to get true. Okay, and then we're taking the intersection of these two, right? We're taking intersection of these two. When do they evaluate to true? When does an AND statement evaluate to true? When both are true, right? So I need both of them to be true, and that's the case here, that's the case here, that's the case here. So these are the three cases, and the other ones should be false, okay? So these are the only cases I get true, and everything else would be false. Okay, another case of and is true only when they're both true. So A true, C true, we're looking for that. There's one here, there's one here, and then I can't find any other place, okay? So A is true only here, but among only these two are the cases when you have true, right? So this gives you true and true there. Everything else is false. Okay, B bar and C, that would be when B itself is false and C is true, so there's one here. FT, that's what we're looking for. There's another FT here, so these are the two cases that it's going to evaluate to be true. Okay, everything else is false. Okay, now when you're taking the union is OR. The logical operator used to define a union of two sets is OR. So usually it's going to give you true unless you have FF, right? So when do you get FF? Here and here. Oh, okay, you have quite a lot. Oh, there's another one here. Okay. So these are the cases where it's F. And all the other cases will give you true. Okay, and now compare this column here with this column because that's the left side and that's the right side. TFT, FFF, TF. TFT, FFF, TF. So this truth table shows that the two sides are the same. Okay?